Hello everybody. We have been discussing the solution of Poisson equation using the Green's function technique. So let me remind you a part of it. And we also said that though we are discussing this in terms of Poisson equation, which is a valid case for the electrostatics and magnetostatics, this method will work if you have a similar setup with any linear differential equation, linear partial differential equation. So the Poisson equation is grad square phi equals minus rho by epsilon naught. So this is, just let me remind you again, this is a linear equation and inhomogeneous equation. Inhomogeneous means that I have a term which is non-zero and does not contain phi, which is what we are trying to solve for. So you are trying to solve for this. And this is the source which is known. Where it is known? In a volume. What else? Boundary conditions. That is also known. Now, this is the question that we are asking. The way we answered it is, of course, using Green's method. So, we introduced something called a Green's function, which is a solution of an equation which has the same operator the solution we call G, but a delta function source. And as we have seen, the boundary condition for G is chosen according to our convenience. Further, we did one more thing. We said that we can break G into two parts. One of these, so let me write G, so that is x prime. One of these I call G prime, other I call F. At this point, I should remind you of the setup. The setup is that I have a finite volume V, which is surrounded by a surface S. So this is the setup for our original Poisson equation. So let me keep the setup at the place of the Poisson equation here. So I have a finite volume V which is surrounded or covered by a surface S. Okay, the boundary conditions are the conditions known at Cs, and the sources are known inside the volume, so at V. Okay, now as we are writing down a different equation which is of the Green's function, we say that this for a boundary at infinity. So that the boundary is at infinity. In 3 dimension, we'll choose the value of the Green's function to be 0 there. So this only depends on the operator. So this, in case of Laplacian, is mod of x minus x prime. This, on the other hand, depends on the boundary. So G has a boundary condition, F will depend on that boundary condition, and F is a solution of this equation with that boundary condition. So the boundary condition will be on G, that is what I will choose for a given problem or a given type of problem. Once I choose the boundary condition of G on G, G prime is already known, so this is depending on the operator. We saw how to get to it in the last discussion. So this is G prime is known, so boundary condition on G directly gives me a boundary condition on F, and I use that boundary condition with the solution of Laplace equation to get what is F. Once I know F, I know G prime, so I know capital G. What do I do? Okay, so let us now choose a particular type of boundary condition, because that is what we will discuss today mostly, which is Dirichlet boundary conditions. As we have been saying, that the choice of the boundary condition on G is on us, and in this case we choose this equals 0 at boundary. So as a consequence, we need to know phi at the boundary. Okay, so that will be enough. If I do all these, now the general solutions, the solutions to phi. So till now I have been dealing with solving a problem that I created, which is this one. But we are interested in solving the original Poisson equation. So the solution for that Poisson equation now can be written this way. And as I said that today we are discussing only the Dirichlet boundary condition. So I am only writing for the Dirichlet boundary condition. We'll be not discussing the Neumann or Cauchy any further in this course. Obviously, you need to be get familiar with those, but in the discussion sessions we will not be discussing. So this is over a volume V. This is over the surface which is enclosing the volume, and what all I will have here is phi prime is the phi. Okay, so let me not write phi prime, you may consider it derivative. So it's a phi s at the surface, obviously, because that's a surface integral. So what does it give us? So we'll see some examples today, but let's understand what has happened. This is only we have discussed last time's things so far. So we have this Green's equation, which gives me the solution of which is Green's function. And we said that the solution can be written in terms of two parts. So one is always 1 by mod x minus x prime if the operator is Laplacian. The other will depend on the boundary and what boundary condition I choose. On capital G, grad square f equals to 0 with that boundary condition will give me what is capital F. Once I know capital F, f plus g prime is my boundary, is my Green's function. And all I need to know of G is to know what is the boundary condition on F. And what is the boundary condition on F comes from the boundary condition on G itself. So if I choose a Dirichlet boundary condition, which is whatever at my boundary, and this boundary will be chosen to be the boundary of the original problem. So the original problem, which is this, has to be a boundary condition, obviously, to solve a partial differential equation. And whatever that boundary is, whatever the geometry of that boundary is the same for when I say capital G equals to 0. So which also means that, so this we call the Dirichlet boundary conditions, wrote with a suffix D, but because we are dealing with only Dirichlet Green's function today, we are not writing the D explicitly. So everything is Dirichlet for today. So F depends only on the shape of the boundary, or should I write geometry of the boundary? Remember, this is the same boundary that is of the original problem. So because that boundary is known, now I know what is capital G in principle. If I am good in mathematics, obviously, solve for Laplace equation, use that boundary condition, I know capital G, and then I can write down the solution for phi. So solving for phi, apart from doing these integrals, which may or may not be trivial but can be doable, solving for phi boils down to solving for f given the geometry of the boundary, and f follows a Laplace equation. So let me write it here. Solving for phi boils down to solving f when grad square f equals 0. So that's a Laplace equation plus same boundary as the original problem. So this is very This is what simplification the Green's function gives you. Okay, so now saying all these, let us look at applications for this. Now it's obvious that sometimes we even don't need to solve the Laplace equation. We can use some certain symmetries of the system to solve for these boundary conditions, solve for f. Okay, so let us consider an example. It's a point charge q naught at a distance d from an infinite conducting plate. Kept at a zero potential. Well, when I say zero, kept at a zero potential, this is equivalent to grounded, right? Because ground is usually taken to be zero potential. So this is a grounded infinite conducting plate in front of which you have kept a point charge. So probably this problem you have seen infinite number of times now, but still let us look at in the perspective of the Green's function technique. So I have this charge which is at a distance d, and immediately you see that if I draw a perpendicular to this, so that is that along that perpendicular the distance is calculated, but that gives you a symmetry axis also. So this is also a symmetry axis of the problem. Because if I go anywhere around this line, if I rotate the system, you will see the value of the potential cannot change. What is G for this? So this is, by the way, this is the original problem. So I can write rho here. This is q naught times delta x minus x1. x1 is related to the position of the charge. So we have to really choose an origin for this coordinate system, and then we can talk about what is that in terms of the origin. Now, let's see what are the symmetries that I have in the system. First of all, let us choose an origin. Obvious choice of the origin is here, where that perpendicular intersects the plane. So I can choose this to be my xy plane, and this as z axis. So then x1, which is the location of the charge, is essentially dz cap. And if I want to calculate the potential at any point in x, you see my charge is here. So this is the location of the charge q naught, which means my volume is this. And my surface is the grounded conducting sphere, sorry, grounded plane, because beyond that I don't have anything that I can measure, but at the plane I am given what is the potential, which is 0. So if I take any other point where I want to calculate the potential which is inside my volume, so that x is essentially so one thing I realize that I have a symmetry in the problem about z axis. In principle, what you now need to do is to solve the Laplace equation of f by demanding the at the surface g is having a certain value. So let's see what is g at the surface. Z equals to 0 by definition at the surface. So g, and so gx, so this I take a vector at the surface. The radius vector at the surface. Radius vector is one which starts from the origin, if you remember. This x prime is 1 by s minus x prime plus I know what is the value of phi in my original problem. The is given to be 0 at the conducting plate. So that corresponds to a Dirichlet boundary condition. Even if I am using a Dirichlet Green's function, so this is equals to 0 at the boundary. Now for this case, it is easier if I use a guess to find the form of f. And that is, it used to be k by s minus, or because I'm choosing f, so let's write this first, x minus alpha x prime. Okay, now so if I use that there, this x has to be replaced by s now, because I'm doing it at the surface now. Now, what is the denominator in the left hand side? This is a square plus x prime square minus 2s x prime. And if I consider the angle between them, what is the angle between them? Well, x prime is this vector, and s always lies on the surface, so the angle between them is 0. So this term I don't need to write down. Square root of this is mod x minus x prime. So if I just square that, so I get s prime plus x prime square. The right hand side I get a square plus alpha square x prime square. You may think what I have done is I have written it this way. That is quite legitimate to do. And then I have squared them. So I get this, and I also get k square equals 1. For this to satisfy. You may be asking, how can I just guess a solution and then figure out what is capital G? And once I have been successful doing that, then you will see that the beauty of one theorem that we proved last time. So what do we get here? What we get here is that either, so alpha square is plus or minus 1, and I'm sorry, alpha is plus or minus 1, and k is also plus or minus 1. Okay, and remember that you have to satisfy this. This is not equals G anymore. So I have to satisfy this. So let's see what I can get. So let's choose k equals 1. And alpha equals 1. So what happens to G now? So G x prime, k and alpha both are 1. So I put, okay, so I completely remove G from the equation, but I can keep it here. So this is G x prime, if you remember, was 1 by mod of x minus x prime plus k by x minus alpha x prime. Right, so this was G. So if this is my G, k equals to 1, alpha equals to 1, okay, so k equals to minus minus 1, alpha equals to 1. So let's take that choice. So what I get for G is that G is 1 by mod x minus x prime minus 1 by mod alpha equals to 1. So this is x minus x prime again. So G is 0 everywhere. It's a trivial solution. Obviously, that is not the case. So let's choose k equals -1, alpha equals -1. So then I will get a g which is x prime. This will obviously, this is g prime, and this will be alpha -1. So this is x plus x prime. Well, that's a legitimate solution, because see what happens if I put these things at the boundary, then you will see that this is going to 0 at the boundary. Okay. How do you see that? Well, obviously this it will satisfy, and if it satisfy that, it will be 0 at the boundary, because that's how I get those. Now once I got such a solution, then I am done, and that's the beauty of it, because G is the solution of its own Poisson equation, which is here, given the boundary condition and that G equals to 0 at the boundary, and that solution is unique, that we proved last time, which means that once I have got such a solution, it's unique. So what is rho? Sorry, what is phi? Now it is trivial to get what is phi. Just put it inside our phi generating machine, which are a couple of integrals. First, there is a volume integral, and the volume integral I will put this now as my g. My rho was q naught times delta of x minus x prime, and then I have a surface integral which is del g del n prime, which I have not calculated, but at the surface phi equals to 0. So this time 0 dA prime. So obviously if I multiply anything by 0, it's going to be 0 only. So what I get here after doing the integrals, charge is at 1, and that's all. There is a catch here. I had a volume integral over a certain volume V. It's not a volume integral which goes to infinity. But then how come I do this delta function integral? Because for the delta function integral to work, the volume integral has to go to infinity. I can do that because this x1 is guaranteed to lie inside my volume. So because I am not introducing any charge here which is outside my volume, so let me write it here explicitly. I can do the above volume integral by shifting the integral limit to infinity. Why is this? This is because x1 is guaranteed to be so remember x1 is the position of the charge in my problem, in my Poisson problem, and that charge is obviously inside my volume. That's how the problem is defined. So if that is inside my volume, I don't have only one charge. If I would have had 5 charges, all 5 charges are also inside my volume. If all the charges are inside my volume, there is nothing else outside. In terms of when I look at in terms of rho, then this volume integral over the outside is 0. So that is why I can push this boundary to infinity. That also we discussed briefly last time, but here we see it in effect explicitly. But now I can also see these two integrals in a little different way. So I can write this just by doing some mathematical manipulations. I can write this in terms of two integrals. In both cases, the Green's function is only this. And then I have x minus x1 plus another integral. You see the Green's function remains as it is. The density now is this. Okay. The first integral is exactly the same. In the second integral, what I have done is I have used the property of convolution where I can change the variables. Okay, let's not look into it that way. But you see, if I do this integral, the second integral, I will get minus 1 by x plus x prime, because now so these are x primes. Sorry, x primes will be replaced by x1. Yeah, so these are x primes. Sorry. Now x primes will be replaced by x1, so I will get exactly the same solution as this. This is the case for 2-point charges. One at x1 charge q0. I'm sorry, these are q zeros, not rho zeros. And other at minus x1 minus q0. Right? So this essentially is the case in the following case, that this is my xy plane now. Sorry, this is xy plane. Z axis. Two charges. And the potential for these two charges is what the potential that you got for the case where I had this grounded infinite conducting plane and one charge here. Immediately you learn one thing, that given, so message, this is a very important message, given a solution, the charge distribution and the boundary conditions are not unique. Now this also gives us a new way of looking at the problem, which we know as the method of images. So this is the origin of the method of images. So what do you do in the method of images? Imagine that I am said that, okay, so this is let's look at the same similar type of problem. I am said that there is a charge of plus q kept here, and there is a charge of minus q kept here. Find out, and there is an infinite grounded conducting plane there. Find out the potential everywhere in the right side volume. What you do is that you say that, okay, first of all, I know that the superposition principle works, so I will do charge by charge. I will first forget one of these charges. I will take that charge. I know that corresponding to that, I can remove the boundary and put another minus q charge over there at the same distance from the boundary. If I solve without the boundary and that only the plus q charge up here, if I put this minus q charge there and solve for the potential, I'll get the exact same potential in the right hand side. Then you say that, okay, so now I can repeat the exercise for the minus q charge. So for that I need to put a plus q charge here at the same distance from the boundary again, and I can solve the potential for these two charges, and once I am done I can just add these two potentials. Or what I can do is that now I have these two charges and their images. I can solve the problem for these four charges. So that's the celebrated method of images. That's a very trivial example with the method of images, but it just comes out of the Dirichlet boundary condition. Exactly this the problem that we have discussed here. Okay, so let us discuss very briefly another type of boundary condition. So this is my example 2. And remember that all that will change for a Green's function is the shape of the boundary. If the shape of the boundary changes, we are dealing with Laplace equations, we will get a different Green's function. Okay, and this is probably you have already done. So let us consider the shape, the boundary shape. sphere. And the obvious choice of origin is at its center. So I call the sphere is of a radius a. So if you change the radius to anything else, so that a parameter that will come in your Green's function will change to anything else. Now what is the geometry of the problem? So I have this sphere, so I draw a circle which represents my sphere. And I have chosen the boundary here, sorry, the origin here. Okay. Mostly for this type of cases, you deal with an exterior problem, which means your volume is here outside the sphere, and one surface which is enclosing the volume is the surface of the sphere. The other surface may be at the infinity. You can also deal with an interior problem where you are dealing with the surface inside the sphere. Okay, so let's say exterior problem. So then you choose your point charge outside for the Green's function, and so that you can say that vector to be x prime. Conveniently, I have put my point charge along my x-axis. That is because I can choose the direction. That direction, that is absolutely which direction I call x, y, and z for the sphere. It's absolutely of my choice. I have chosen it as a horizontal direction now, and say this is my x. So I will always have to define an angle which is the angle between these two. So, or you can say that x cap prime dot x cap is cos of delta. Now I will leave it to you, because this probably you have already seen in your earlier courses. The Green's function in this case can be written in the following way: x minus x prime is nothing but x square plus x prime square minus 2x prime cos delta, and that entire thing to the power half. That gives you the magnitude. This minus, so let me bring it to a little more to the left. This minus, now because it's a sphere, this will be a little bit more involved. A is the radius of the sphere, remember. Okay, this is the Green's function if the boundary is a sphere, and delta is the direction, delta is the angle between the direction of x and x prime. I have not gone through the detail of calculating this. This you will find in any book, and you know the method to do it, you should be able to do it for the sphere. Once I know this, I can calculate del g del x prime. Why I am doing this? Because remember, in the surface term of the Green's function solution had this thing, and this I have to calculate at the boundary. So that is x prime equals a. So it doesn't matter whether you write del g del x at a or del g del x prime at a, it will be the same. Just you have to replace x by x prime. because if you look at this Dirichlet Green's function, it is always symmetric about x and x prime. If you change x and x prime in this expression, nothing will change. And then now I can write down for the case of sphere, if the boundary is that of a sphere, you have to be careful while writing the first volume integral, because that volume can be of the exterior problem where the volume is outside the sphere, or the interior problem where the volume is inside the sphere. Surface is always the surface of the sphere. See, the direction of x or x prime is towards the outward normal. So del g del n prime is nothing but the del g del x prime, which is written over there. So I just write it as del g del x prime. This is phi at a theta phi. So I write it in terms of polar coordinates. With the keeping it at the surface, which means x equals to a, r equals to a. Now, let us say that, okay, so this is all kind of hypothetical so far. So let us solve a problem, an example, and you will see a few in your assignments. So if I say that, okay, so now I have a spherical boundary. So this is spherical boundary. It's grounded. I'm sorry, it's not grounded. So the potential is not 0, but somehow it is kept at a constant potential V0. Okay. And what is the condition on rho? No charges outside. So I have a sphere. Better be conducting, it will be easier. But anyway, I have a sphere which is kept at a constant potential V0. And I am seeking for an exterior solution of the problem, which means that I want to know what is the potential at any point outside. The origin I have chosen to be here. So I want to know what is the potential at x. X is outside the sphere. Okay, so outside there is no charge. So the first term is 0, rho is 0 everywhere. So phi x is entirely given by the second term, which is minus 1 by 4 pi. I can write this dA prime is the integral over the surface of the sphere, which is 4 pi a square dA I'm sorry. See, the surface of the sphere, what is the volume element or the area element? The area element of the surface of the sphere is, so let us write it down. It's a square and then d theta and d phi. But there is a symmetry about phi, so that gives me directly 2 pi. And then I have sine theta d theta. This is just nothing but dA. So in any point here is a square 2 pi. sine theta d theta. I have to integrate over theta. We'll see that if I choose a symmetry, my z-axis about this, then there is a symmetry about phi. So I can directly do the phi integration. The phi will not appear anywhere. I will see that. I have not done it yet. So I am just going ahead and just writing that the phi integral is done. So that gives me a 2 pi. So the only integral remains 0 to pi on theta. Okay. And better write d theta later because I have not written the integral yet. What do I have for the integral? Well, the potential is kept at constant V0 at the boundary, so that can go outside. And I need that V0 goes outside, so this has gone outside as V0. So del G del X prime is what I have to write, which is given here. So A x square plus A square minus 2ax cos delta to the power half, and here I have a square minus x square and d theta. Okay, see, it's cos delta over here, so I have to figure out what is that. That is not done yet. Now I have chosen my x like this, so which means that theta equals to 0. So the vector x can be written by x, theta and phi. X is the rho, theta and phi, so x is the amplitude of vector x, theta and phi are the directions. Similarly, x prime can be written as so if I do that, we will agree that x cap is nothing but cos theta sine phi I cap. I is the x-axis of the horizon, one of the horizontal axis. I am sorry, so these are all going. So sine theta cos phi I cap plus sine theta sine phi j cap plus cos theta k cap. But what I have done is I have chosen my x cap along the k cap axis, so which means that theta is along the k cap axis, so x cap is basically k cap. X cap prime is sine theta prime cos phi prime so remember cos delta was x cap dot x cap prime, and now I can write them in terms of all these sines and cosines. So I will get sine theta cos phi sine theta prime cos phi prime in the first term. But you see that these terms are 0, so I will just get this So I will get cos theta time cos theta prime. Cos theta is 1, so this is essentially cos theta prime. So when I do this dot product, I have chosen theta to be along the k direction. So theta is essentially 0 degrees. So sine 0, theta is 0. This sine 0 is also 0. So these and these terms are 0. This terms is 1. So this gives me just k cap. So when I do the dot product of x cap with x cap prime, the first I cap and j cap does not give me any contribution. The only contribution comes from k cap, and that is just cos theta prime. So which means now, so these are all theta primes, I'm sorry, because we are doing the integration on the prime coordinate. So this cos delta can be replaced by cos theta prime. So finally, I get my phi x, which is, let's see what has happened here. So that's 2 pi can cancel out. A square will give me a. So this is minus b0 a by 2. This is not x prime. I think that is the integral. Okay. So please verify. Please check. And also do the integral. If you do the integral, you will see this will come out to be something very familiar. So that I will not do, but just wanted to demonstrate to you how this works. So in this particular case, it was all contribution came from the surface term, though there was no charge inside the volume of concern, that is the exterior volume. All the contribution came from the fact that there is a spherical surface where a potential is kept constant. Okay, so that is the essence of the way of solving electrostatics and magnetostatics problem using the Green's function technique. Let me go a little bit to discuss about what happens in electrodynamics. And this is going to be a very, very superficial discussion. But if you have got the idea, then you will be able to figure it out. So in the electrodynamics, we looked at this operator, which is 1 by c square del 2 del t2 minus grad square. So all that I have to do now for the case of electrodynamics and Lorentz gauge, that the problems in electrodynamics in Cartesian will look like the following. It will have this form. You see, if I want to come to statics, everything, the t dependence goes away from everywhere, and in the box square operator, the first term goes away, so the left hand side becomes minus grad square psi. So that's essentially again the Poisson equation. Now for this corresponding corresponding equation for Green's function we know how to write down. All that I have to do is I have to change this to the Green's function. Now this will depend on x t, x prime t prime, and in the right hand side I will have 4 pi x minus x prime t minus t prime. The rest of the method is exactly the same. First you have to solve for the case of the same equation with, here remember that I have not chosen the boundary. So what is about the boundary here? So it's a boundary is not only that you have to tell about a volume, you also have to tell that when you have measured the potential on that volume. So the boundary is measuring the potential on the surface of a volume at a given time. If I don't tell the time, or it's actually the time interval, so in between this time and that time, the variation of the potential has to be known at the boundary. If that is given, then this problem can be solved. And remember that also, so you are talking about a volume, you are also giving a time interval. So it's a volume, the surface which is surrounding this volume, and if this you assume to be a clock, then you are saying that between this time and that time I am given every information inside the volume and on the surface. So then only I can solve this problem. Okay, that is about the boundary condition. And what will you do that? So well, first you will say that okay, I will throw my volume to be infinity, consider all times, and then I solve this equation and call that G prime. And that G prime, you can again use the Fourier transform technique to get the G prime. The integral is a little more complicated in this case. This comes out to be the following. It has the classic x minus x prime in the denominator, but the numerator now involves time. So the numerator is a delta function. It's a little complicated delta function. It's t prime minus t plus minus, or rather minus plus. So there are two solutions to this. So I call those G plus minus. So when you take the plus, you have to take minus from here. Okay. So what is the interpretation? The interpretation is that t prime has to match with either t minus that or t plus that. Okay. So if I want to figure out what is psi at a given x and t, now see this has two terms. So one is the surface term which I am not writing here. You can assume that surface term to be 0, throwing the surface at infinity. But then I have plus this term as the, this is how I write the solution once I have got the Green's function. And what I am saying is that the Green's function is for a problem where my boundaries are at infinity. So then this is equals to, I can do the T integral because I have a delta function over there. So what happens when I do the T integral? This remains as it is, but rho now has to be evaluated at some T plus minus, where T plus is given by T minus. Remember that the left hand side is a function of T, so it should be given by T minus x prime by C, and T minus is given by so this is called advanced solution and this is called retarded solution. So what is happening here? Let's see. So I have the charge density. So I am asking the following question. So I have one point here, say at x, another point here, say at x prime. X prime I have a charge, so that I call rho at x prime. Okay, it's also a function of t, so let's call that t prime. I'm asking the question, what is the potential at phi? So at time t. What this is telling you is, you see, this is the exact same looking case for the electrostatic solution. But there is the fact that this rho has to be calculated at an earlier time. What does it mean? Well, if we calculate the distance between this point to this point, this distance is mod of x minus x prime. And the time a light signal takes to go from x prime to x is given by x minus x prime by c, because c is the speed of light. So what it is telling you is that to know the phi here, you need to know what is rho, which was there this much time earlier. So that is the effect of this rho is felt at this point at phi, for phi at a later time. So that's why it's called a retarded or later solution. Okay. There is also an advanced solution, as you can see here. It was used by Wheeler and Feynman to explain certain things, but finally it did not work out very well. So we'll not even talk about it. But this is the meaning of the retarded and the advanced Green's function. Now this can be used now to solve for electrodynamics problem, particularly the problem of propagation, generation and propagation of radiation. But that's it. That's all that I will discuss with you in this course, and I have also uploaded the assignments, so please go through the assignments. What we have done today is looked at the electrostatic Green's function and looked at it for two different boundaries and kind of sketched how we solve the boundary value problems with the Green's function. What is its connection with the method of images? We also looked at very briefly the Green's function for the electrodynamics problem. What is the equation that you solve to get the Green's function? What is the solution that you get? And what is the